Hello students, in the previous lecture we have discussed about capacitors, various types of capacitors and most importantly the principle of a capacitor. In this session we will discuss the combination of capacitors. Various capacitors can be combined either in the series grouping or in the parallel grouping, right? So let's start with the series grouping of capacitors. So, first article we will discuss the series grouping. Now, capacitor, as you are aware, the symbol of a capacitor, it's like this. It's the symbol of a capacitor represented by two parallel lines, right? It's the symbol of a capacitor having fixed value of capacitance, say C. Now, let us consider three capacitors having capacitances of C1, C2, C3 to be connected in series. Series means end-to-end connection. So, two or more capacitors are said to be connected in series if the charge across the plates of each of the capacitors remain constant. So, that's the condition for the capacitors to be connected in series. So, end-to-end connection, that is the case of series grouping. So, let's draw the diagram. And I am taking the illustration of three capacitors. These are the three capacitors under consideration, and suppose they are connected in series. This suppose capacitor of capacitance C1, C2 and C3 respectively. Let these points be A, B, C and D, right? And suppose the points A and B, they are connected to a source which is maintained at a constant potential difference of V. This is a source. This is a positive terminal, this is a negative terminal. Now this is end-to-end connection. So the charge across the plates of each of the capacitor would be constant, and that's the mandatory condition for the capacitors to be connected in series, right? Suppose plus Q charge is over here. So negative charge will be produced on the inner face of the other plate. Here the positive charge will get neutralized from the electrons coming from here. So here it will acquire the equal positive charge. Again, negative charge will be developed on the inner face of the other uncharged conductor. So again, the positive charge developed on the farther face will get neutralized from the electrons coming over from here. So it will again have positive charge. It will be acquiring negative charge. And this positive charge will develop, if it is earthed, then the positive charge developed on the farther face will get neutralized. So that's the concept involved. We all are aware of it, right? Suppose the potential difference across the first capacitor between the points A and B is V1. Let us consider the potential difference across the second capacitor is V2. And across the third, that is between the points C and D be V3. These are the potential differences across the plates of the capacitor having capacitances C1, C2 and C3 respectively, right? And basic formula we all are aware, Q equals to C. That's the formula involved. So, before starting the mathematical part, again I am repeating, two or more capacitors are said to be connected in series when they are joined end to end. In such a case, the charge across the plates of each of the capacitor remain constant. So, point to be noted is that here charge is constant across each of the plates. It will be constant. Right? So now let's find the formula for the equivalent capacitance of the series grouping of capacitors. For that, what we'll do is, let's consider point A and B, V1. It is the potential difference V1. So VA minus VB, it is considered to be V1. Potential difference between the points A and B is considered to be V1. This is the potential difference which is considered to be V1. And as per the formula, it is Q by C1. Put this as equation 1. Since Q is equal to CB. Obviously, therefore, V1 it can be written as Q divided by C1. Q is constant, right? Similarly, potential difference between points B and C. VB minus VC. It is considered to be V2. And it will be Q by C2. Right? And potential difference between the points C and D. Vc minus Vd, it is V3 and it will be equal to Q by C3. Also, potential difference between the points A and D, VA minus VD, it is equal to V. Between the points A and D, the potential difference comes to be V, which would be equal to Q by C series. C series is the equivalent capacitance of the series grouping. So what I mean to say is that this circuit is equivalent to this circuit. Like this. I have replaced the three capacitors with a single capacitor having capacitance of C series. Charge would be same, plus Q, this is minus Q, and potential difference between the points A and D, it is V. It's absolutely okay. So it is the equivalent diagram of the original one, right? Now the final step, what we do is we add 1, 2 and 3. Let's see what we get. So adding 1, 2 and 3, we get V1 plus V2 plus V3. V1 plus V2 plus V3. If you add minus VB plus VB get cancelled, minus VC plus VC get cancelled, so we will be left with VA minus VD. Simply add 1, 2 and 3. And over here Q is common. So we can write 1 by C1 plus 1 by C2 plus 1 by C3. Fine. Also from equation 4, VA minus VD is equal to V. So V is equal to Q 1 by C1 plus 1 by C2 plus 1 by C3. And V is equal to Q by C series from this. This is equation 4. So we get Q by C series is equal to Q 1 by C1 plus 1 by C2 plus 1 by C3. Therefore, we conclude that 1 by C series is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So this is the formula which we will use for the series grouping of capacitors, right? So before we proceed with the next topic, we must understand certain important points involved in the series grouping of capacitors. So first and foremost, what we have discussed is, in the series grouping, charge is constant. Charge across the plates of each of the capacitor must be constant. Okay, let's conclude it. So this statement is known as the law of combination of capacitors in the series grouping. So this law states that when two or more than two capacitors are connected in series, then the reciprocal of the resultant capacitance of the series grouping is equal to the sum of the reciprocals of the capacitances of the individual capacitors. So that's the law of series grouping. Again I repeat, this law states that the reciprocal of the resultant capacitance of the series grouping of capacitors is numerically equal to the sum of the reciprocals of the capacitances of the individual capacitors. So we can extend this expression for n capacitors connected in series as well. So therefore, for n capacitors connected in series, we can write it like this. It is equal to summation I equals to 1 to n 1 by Ci. So for n capacitors connected in series, this will be the formula, right? Now some important theoretical conclusions. First, as I stated, charge across the plates of each of the capacitor must be constant. This is the first point. Second, the potential difference across the capacitors having different values of capacitances is different, right? So V is different across different capacitors having different values of capacitances. Third, as Q is equal to CV, since Q is constant in series grouping, therefore CV is constant, which implies that V is inversely proportional to capacitance. What I mean to say is that greater or larger the value of capacitance of a capacitor, smaller will be the potential difference across it, and vice versa. I repeat, higher or greater the value of capacitance of a given capacitor connected in series, the smaller will be the value of potential difference across its plates. Right? So this is a very, very important conclusion. And lastly, you can well observe the resultant capacitance of the series grouping is less than the minimum of the given value of capacitance in the individual capacitors. So what I mean to say is that suppose the value of this capacitance is 1 microfarad, the value of this capacitance is 2 microfarad, and the value of capacitance of this capacitor is 3 microfarad. So out of these three capacitors, it is having the least value, 1 microfarad. So in series grouping, the resultant of all the three capacitors connected in series would be less than the minimum of the given value of capacitance. So here C series, the series combination will have a resultant capacitance which will be even less than 1 microfarad. You can easily check it by doing this formula, right? In case of two capacitors connected in series like this, C1, C2, 1 by Cs would be equal to 1 by C1 plus 1 by C2. So it is preferable to directly make use of this formula, C1, C2 divided by C1 plus C2. So Cs is less than C1 as well as Cs is less than C2. This is what I have stated over here. So in the series grouping of capacitors, the resultant capacitance decreases. It is less than the minimum value of the given capacitance. So this was all about the series grouping of capacitors, right? The other grouping is the parallel grouping of capacitors. So parallel grouping of capacitors, again we will take the illustration of three capacitors. Suppose we consider the same example, that is we have considered three capacitors having capacitance of C1, C2, C3 and connected in parallel across a source. So in this series, the capacitors are connected end to end. In this series, the capacitors are connected end to end. While in parallel combination, in the parallel grouping, the capacitors are connected across like this. This is the first capacitor, this is the second capacitor, and suppose this one is the third capacitor. They are connected in this particular manner across, and the combination is connected to a source. Suppose a potential difference V. Suppose these 2 points are A and B. First one, it's having capacitance C1. Second, suppose it is having capacitance of C2. And third one is having capacitance of C3. Now look, you can safely conclude from the diagram that two or more capacitors are said to be connected in parallel if the potential difference across the plates of each of the capacitor is same as that of the applied voltage. This is the applied voltage, isn't it? This is the applied voltage. So the PD across C1, it is also V. The potential difference across C2, it is V, and it is also V. Why? Because the plates of each of the capacitors are connected between the points A and B. And the voltage is applied also across A and B. So this is a very, very important statement. So two or more capacitors are said to be connected in parallel only if the potential difference across the plates of each of the capacitor is same as that of the applied voltage. So that is when the capacitors are said to be connected in parallel, right? Suppose its equivalent circuit diagram is like this. As was in the previous case, here also we consider all the three capacitors, their parallel grouping is replaced by a single capacitor, C parallel, having capacitance of C parallel. This point A, this is point B, and this is the applied voltage. This is the equivalent circuit, right? We need to find C parallel in terms of C1, C2 and C3. So point to be noted is that here V is constant. So here this will act as a junction. It will send some charge, and net charge sent by the source will get distributed amongst these three branches. Suppose Q1 is a charge over here. So here negative charge will be induced. Here it is Q2, here minus Q2. Here suppose the charge on this plate is Q3. So on the inner face on the other plate it will minus Q3. And the positive charge so developed on the further face will get neutralized as it is earthed. It is understood. We have discussed the principle of a capacitor, right? As we all are aware, charge is conserved. So net charge sent by the source is Q. So as per the conservation of charge, net charge would be given by Q1 plus Q2 plus Q3, isn't it? And the basic formula is Q is equal to CV, isn't it? So Q, this is the net charge. This is the net charge. So what's the relationship between Q, C and V? Q would be equal to C parallel multiplied by the common potential, which is equal to the applied voltage. What is Q1? It would be equal to C1V. Q2 would be equal to C2V. Q3 would be equal to C3V. So V can be taken common over here. C1 plus C2 plus C3. And over here, C parallel into V. Now since some final value voltage is to be applied, so V can't be 0, which implies that C parallel is equal to C1 plus C2 plus C3. So this is the formula which we will be using in order to calculate the net capacitance in the case of parallel grouping of capacitors, right? So let's conclude this statement. This is actually the law of parallel grouping of capacitors, which states that when two or more capacitors are connected in parallel, then the resultant capacitance of the parallel grouping of capacitors is given by the sum of the capacitances of the individual capacitors, right? So we can extend this for n capacitors connected in parallel. So for n capacitors connected in parallel, what you get is C parallel, it will be equal to summation I equals to 1 to n Ci. So this is the generalized expression, right? So let's discuss some important points as was done in the topic of series grouping, right? There are 4 important points to be noted down. First is 2 or more capacitors are said to be connected in parallel only when the potential difference across the plates of each of the capacitor is same and is same as that of the applied voltage. So what I mean to say is that V is constant. In the series grouping, charge is constant, but in the parallel grouping, V is constant, right? Second, the charge across the plates of capacitors having different values of capacitances is different. So it's Q1, Q2, Q3 over here. So Q is different. Or the charge across the plates of capacitors having different values of capacitances would be different. So here the condition becomes exactly the opposite to that of series. In series, charge is constant, V is variable. Over here, in the parallel grouping, V is constant, charge is different, right? Third, since Q equals to CV and V is constant, in the parallel grouping V is constant, therefore Q is directly proportional to C. What I mean to say is that the larger the value of capacitance of a capacitor, the more will be the charge stored in it. In the parallel grouping, the greater or larger the value of capacitance of a capacitor, the greater will be the charge stored in it, and vice versa, right? Next one. Now look, it is given by the sum of the capacitance of the individual capacitors. So obviously the net capacitance of the parallel grouping would increase. Let us give an illustration. Suppose it is 1 microfarad, C2 is having value of 2 microfarad and C3 is having value of 3 microfarad. Right? So this is the maximum capacitance of the given capacitor. Right? So C parallel would be 3 plus 2 plus 1, that is 6 microfarad, which is greater than the maximum of the given value of capacitance. Maximum of the given value of capacitance. So, in the parallel grouping, the resultant capacitance is greater than the maximum of the given value of capacitance. So, this was regarding parallel grouping of capacitors. We can also discuss some simple basic numericals. To start with, we can consider some simple basic numericals. So let's do 2-3 questions related to series and parallel grouping. Right? We'll consider all the capacitors to be identical, each having capacitance C. We'll consider each capacitor to be having capacitance of C. Let's consider a very basic example. Like this is point A, and these are the capacitors which are connected in a manner as shown in the figure, like this. This is suppose point B. All the capacitors are identical, having net capacitance of C. Now in each question we are supposed to find the net capacitance between the points A and B. Net capacitance between the points A and B. What to do is, you can simply stretch it. On stretching, the equivalent circuit would be like this. If you stretch it, the equivalent circuit would be like this. This is A and this is B. Obviously, they are connected end to end. So it must be the case of series grouping of capacitors, isn't it? So as per the formula, 1 by C net, it would be equal to 1 by C plus 1 by C plus 1 by C. How many times? 5 times. So what do you get? 1 by C net is equal to 5 by C, or net capacitance with the points A and B is C by 5. It's a very basic question, right? Let's discuss some other one, interesting one. Suppose this is the case. This is A, this is B. All the capacitors are having capacitance of C. Our objective is to find out the net capacitance between the points A and B. So how to proceed? Let's see. Let's check it out. We need to convert this circuit into a simpler equivalent circuit. So what we basically do is, now look, consider this capacitor. One of its plate is connected to point A and the other plate is connected to point B. You need to consider that path which do not contain any circuit element, right? So one plate is connected to point A, the other plate is connected to point B. Consider this capacitor, second one. Again, one plate is connected to point B, while the other plate is connected to point A. Consider the third one. Again, one plate of capacitor 3 is connected to point A, while the other plate is connected to point B. Remember, you have to consider the path which do not contain any circuit element, right? So what we conclude is, all the three capacitors, their plates are connected across the same two common points A and B. So this circuit can be redrawn in the following manner. This is point B, this is point B. So all the three capacitors are connected between the same 2 points. Isn't it? All the capacitors, this first, second, third, all having same value of capacitance, C. So it is actually equivalent to 3 capacitors connected in parallel, isn't it? So in parallel grouping we are aware the formula is C1 plus C2 plus C3. Each being equal to C, we get thrice C. So that's the way of proceeding with such numericals. These are some very basic. basic questions, right? Let's discuss another example. Let us discuss another example. Suppose this is the case. These are the 4 capacitors. This is point A, this is point B. This is given to be like this, and let us consider this to be 3 microfarad, this to be 2 microfarad, this to be 5 microfarad, and this to be 10 microfarad. Right? We need to find out the net capacitance between A and B. This is our objective. It's a mixed grouping. Some are connected in parallel while their resultant along with the other capacitor is connected in series. So what we'll do is, we'll consider this one first. We'll consider this one. Start with those components which we are very much sure. There shouldn't be any dilemma. So it is pretty clear that these 3 are connected in parallel. Just now we have discussed, these 3 are connected in parallel. So the present circuit can be modified in this particular manner. This is point A. It can be modified in this particular manner, right? This is 10 microfarad. This is 3 microfarad. This one is 2 microfarad. And this one is 5 microfarad. This is point B. So it can be redrawn in this particular manner. Now these 3 are connected in parallel. So in parallel we will make use of this particular formula. So 3 plus 2 plus 5, it will give us 10 microfarad. And this one is also 10 microfarad. Now these 2, obviously they are connected in series. So in series the formula is 1 by C equals to 1 by C1 plus 1 by C2. And directly if you wish to do, then C series for 2 capacitors having C1, C2 value are C1, C2 divided by C1 plus C2. So in series, the resultant capacitance decreases. In case both are of same value, the resultant series capacitance will become half of the given value. So it will be actually 5. 10 into 10 divided by 10 plus 10. You can solve it like this as well. 1 by 10 plus 1 by 10. So it would be 10 into 10 divided by 10 plus 10. So it is in microfarad. So it is 5 microfarad. So its equivalent diagram would be like this. This is A, this is B. To see resultant, it is equal to 5 microfarad. I hope you are able to understand these basic questions.